Welcome to the tutorial on pushover analysis and time history analysis. I'm Arvind, research scholar from VIT University Chennai campus. The pushover analysis is a nonlinear static method. It is also a performance-based design. The pushover analysis estimates the global displacement of a structure with less computational effort. The multi-degree of freedom is converted into single degree of freedom to determine the capacity curves in the form of base shear and displacement at the roof. The pushover analysis can be performed by two different methods: capacity spectrum method and displacement coefficient method. The capacity spectrum method is an equivalent linearization approach by FEMA 440 and ATC 40. It converts the pushover curve to spectral acceleration and spectral displacement to get the capacity spectrum. The reduced ground motion response spectrum is converted into acceleration displacement response spectrum, which is ADRS, which is the demand spectrum. The capacity spectrum and the demand spectrum are plotted together. The intersection point is called the performance point. The performance point is the estimate of maximum displacement. The displacement coefficient method has been derived in FEMA 356, a numerical process for estimating the displacement demand on the structure by using bilinear representation of capacity curve and a series of modification factors or coefficient to calculate the target displacement. Again, this method has also been defined in ASCE 4113. The pushover curve is used to determine the effective stiffness and period. When used with response spectrum, gives the spectral acceleration, then converts the spectral acceleration into the elastic displacement to which modifying coefficients are applied to determine the target displacement or the maximum displacement. The pushover analysis gives the performance level of a building based on this curve. Point A is the origin and point B is the yielding point. No deformation or no hinge occurs from point A to B, and it is the elastic region, and point C is the ultimate capacity of the building. From point B to C, the yielding starts, and they are subdivided into three groups: IO, immediate occupancy; LS, life safety; and CP, the collapse prevention. And at point D, residual strength limit of the structure, and at point E, total failure of the structure takes place. The operational level OL, this performance level is from point A to point B. No permanent damage is occurred in this level. The structure retains to its original strength. Minor cracks are allowed in partition walls and false ceiling. Immediate occupancy level IO, no drift is allowed. Elevators can be restarted since there is no damage. Minor cracks are allowed in partition walls and false ceiling, fire protection, and no gas leaks. The immediate occupancy level shows that after the earthquake event, the occupants can occupy the building. Life safety level, some residual strength is available in the structure. The gravity load-bearing element functions. No out-of-plane failure of the wall or tripping of the parapet walls are allowed in life safety. They are not allowed. Some drips can be observed in life safety. Collapse prevention CP, a very little residual strength is available in the structure. The gravity load-bearing element functions. Permanent large drips can be seen, and the failure of partition walls takes place. The hinges are the indicators to show the structural behavior of sequential loss of strength in difference with the performance level. The point of inelastic action of the structural member is called the plastic hinge. Now, these are the four steps involved in the pushover analysis. The first step, we are going to check the adequate capacity of the gravity load. Then we are going to define the gravity load and the pushover at X direction and at the Y direction, and we have to assign the inches and then run the model and check for the results. At the same time, we are going to follow the time history analysis also. So the time history analysis is a nonlinear dynamic analysis. The nonlinear time history analysis is best known for simulating the behavior of a structure under severe earthquake by providing the original ground motion data. Now this method is the best method and provides the accurate results. By default, ETAB has n number of pre-occurred earthquake acceleration data. We are going to take the original acceleration data and apply the ground motion data to the building and check its behavior. I'm going to use the previous model which we used for the equivalent static method and response spectrum method, same model. So now I'll just run the analysis part so that I can check for the gravity adequacy of the building. Okay, the model has been run. So after running the model, the automatically the model locks off so that no changes can be made. So if you want to make any changes, you can unlock the model. Now after the analysis, we'll go for the concrete frame design. Just click here. Once you click, automatically the members are checked. So these are the AST values from top and bottom. I will go for again to check whether verify all members are passed. Now it shows that 72 member failed. So the red color, especially the beams have been failed, and the purple color, the column. So the columns are safe and they have passed. Only the beams have failed. This shows that the building is inadequate to take the gravity load. So now we will unlock the model. We have unlocked the model. Now we'll go for define, section property, frame sections. We'll go for concrete beam and modify its dimension. So we'll provide the depth of the beam as 350 mm and the width of the beam also 350 mm. We'll modify the top bars from 20 mm cover 20 mm. We'll click OK. OK. And in concrete column, we will change the dimensions also. Now this has 450 by 450. We'll change the rebar to 20 mm, 20 mm. Okay. Okay. So we'll check again. We will again run the model. Once the analysis is over, we'll go for the concrete frame design. Click there. Again, it will check whether the member is able to carry the gravity load. We'll go for again, check from verify all members. So all the concrete frame members have been passed, so they are able to carry the gravity load. Now we'll go for define. We will define the functions. So previously we have defined the response spectrum as per our Indian standard. We are not going to make any changes here. Okay, I have to unlock the model. Okay, again we'll go for define. We'll go for time history function. Here choose from file, add new function. I'll just name it as TH as time history. Click for browse, and when you click for browse, go to the C folder where you have installed the eTabs software. So go for C and go for the program files, and in program files go for the computer structures, and computer structures choose the etabs 18, and in that go for the time history functions. For some, if it is not displayed, it will be from text format. You have to choose the all files. So these are the available earthquake acceleration data in etabs. So you can take any of the data and apply the acceleration data to your structure and find the responses, or else you can even download the other earthquake data all around the world from online, and you can apply to your structure and find the response. So right now I'm going to take lat north. I'll click open. So this is the north lag earthquake data. Okay, I will click OK. So we have defined the time history function. Okay. Again, we'll go for defined. This time we'll go for the load pattern. In load pattern, we will add the pushover and the time history load patterns. So PA pushover at X direction. This is also seismic, and 2016 add Y, add new load THX, add new load, add new load. Okay, so we have added pushover at X and Y and the time history in X and Y. We have to modify the functions. So modify the lateral load. So this is at X direction. So we will uncheck all other directions. The importance factor is 1.2. Click OK. Then here again we will check for only for the Y direction. For time history it is in X direction now. This is it in Y direction. So we have modified the corresponding directions for the load patterns. Click OK. Then we'll go for define. We'll go for load cases. So here we have to again modify the load cases to their corresponding load case pattern. So now for running the pushover, we have to add a new load case called gravity. So that is GR, gravity, that is non-linear static. The mass source, we have to take the specified load pattern which we have considered. So now we have to click add. By default, leave the load pattern dead and scale factor 1 because it is gravity. And the load application is also going to be a full load, and it is going to be in Z direction. So it is U3. So click OK. And the results can be saved from final state only. Okay, so all other settings are same. We'll click OK. Now we'll go for pushover. We'll go for modify option. So here we'll go for nonlinear static. Again, this is also mass source. This one we will select. So it is asking to continue the pushover from zero initial conditions or from the predefined. So we have to go from gravity. From gravity we have chosen. Now from here we have to take the load type as acceleration, ux in x direction, scale factor as 1. This is the geometrical nonlinearity. We will take the p delta, and the load application, it is going to be displacement controlled. We'll take the use monitor displacement, and this is at x direction. Click OK. So in results we have to save it as multiple states. So then only we can generate the pushover curve. And for nonlinear parameters, these are the other data available. So the iteration process, it runs by Newton-Raphson method. Click OK. Again, so we will modify the function. This is nonlinear static. Mass source will continue from gravity. Again, this is acceleration at y direction. P delta, displacement control, u2 at y direction, multiple states. Okay. For time history, we'll modify the case. We'll take the time history function as the load case, and this is going to be a nonlinear model. So here we have to take the acceleration at x direction and the function as north lag, scale factor is 1 by default, and all other functions are okay. Then we'll click OK. Again, we'll modify the y direction, that is also a time history. This is nonlinear model. Acceleration, y direction u2, north lag, scale. Okay. So we have defined the load cases and load pattern. Now we have to define the hinges and assign the hinges to the beam and column. So for that, we will select the beam, select object type, beam. We will select all the beams. So 96 beams have been selected. We'll go for assign, frame, hinge. Here we'll take the auto hinge property 0, 0 and 1, two hinge values we have to give. So 0, we'll click add. In here we have to take the table number ASC 41313. We'll consider the concrete beam. So we have selected the beam, so it is flexure. So the degree of freedom is M3, and the corresponding case, which is going to be pushover at x axis, at x direction. We'll click OK. Again 1, we will add same set of functions. Okay, everything is same. M3 concrete beam 41. Okay, so again we will add the same function, but now this time it is going to be at y direction, concrete beam. Okay, at y direction. Okay, so we are going to assign 4 inches in 2 for x and 2 for y, which is 0 and 1. When you click OK, it automatically assigns. So the hinges have been assigned to the beams. Now we will assign the hinges for columns. We'll go for again select object type. We'll select columns have been selected. We'll go for assign, frame, hinge. We'll add. Now here we have to take 4117. Here we will consider the concrete column. sorry, 4113. We'll consider the 4113 table, table 10 to 8 concrete column. So here we have to take P M2 M3, and the case is pushover at X. We'll click OK. For 1, we'll add same function 13 concrete column P M2 M3 PAX at 1. Now at 0 we'll add for Y direction. For Y direction. So we have defined 4 hinge values. So the hinges have also been assigned to the beam and column. Now we can run the model. So before that we have to select all the column and beam and provide hinge overrides. So we have selected all the column and beam. We'll go for assign, frame, hinge overrides. We'll click OK. So hinge overrides has also been assigned to the column and beam. We will run the model. The analysis is over. So these are some warning messages I got. So the first warning message was that like non-zero time history function values will be ignored at the start of the load case. So you can ignore these two warning messages because in the time history function value we will have only the acceleration data and the subsequent time in seconds. So the non-zero values are ignored, so that is not going to cause any problem for us. So we'll ignore the first two warning messages. Now when we go for the third and fourth warning message, which says that the maximum number of null steps have been reached for case pushover at X direction and the subsequent results will not be available. So again in this condition, this is not also going to cause any impact on the result, so we can ignore this warning message also. But if you want to have the 100% the pushover analysis to be run at X direction, you can increase the null steps from 50 to 100 or even to 200. You can increase them, then again you can iterate the model, run the analysis, then you can overcome this warning message. So again this warning message is not going to impact any results, so we'll go for seeing the results. So now we'll go for display. First we will check for the static pushover curve. So this is the pushover curve. So this is the curve. So the maximum is 4437.67 kilonewton. So that is the base shear, and the displacement is 65 mm. So the displacement is I think 66 mm. Okay. So this is the static pushover curve. From linear, again it is changing, it's yielding, and now what, this is at Y direction. So in Y it is 4933.8 is the base shear in kilonewton, and again the displacement is 96 mm. So we'll check for other. So here we can see other methods. So this is the default method which we saw, the static pushover curve. Now we'll go for ACE 4113. So this is the red color is the bilinear curve, and this is the capacity. So here we can see the NTC 2008 target displacement. So here we can find the capacity and the demand, the performance point. So here we can find all other details like bilinear, capacity curve, so it has been displayed. So there are other plot functions also you can choose as per your requirement. For display plot functions, so in plot function we'll go for define this fx. So here we'll select the joint displacement, click OK. The vertical function is base shear value, and at the horizontal we'll select the joint displacement. So this is should be considered at push time history. So for time history, this is the energy dissipated. So I have by default I was considering the push at x. Now we have to change the load case as time history. So this is the time history at x direction, and at the horizontal displacement, and this is the base shear. So this is the uh, energy dissipation that took place. So the maximum is, I think it's 290 kilonewton. So when you change the steps, you can see the steps taking place. So here I will consider the time now. So this is the base shear with respect to the time. So the maximum is at 9.1 second. That is the peak of the base shear value, and at the lowest is 9.4. So here this is the lowest form. Now we'll scale the time history with the equivalent static method. So for that we'll go for display option. We'll go here, show tables. So here we will click analysis result. We will uncheck all of the results and consider only the structure output, and in that we will consider only the base reaction and nodal information. We'll click OK. So to scale down the time history with the equivalent static method, so for time history we'll be having two values. So at x direction, that is maximum and minimum. So we will add both irrespective of their signs. We will just add the values. So 278 plus 363 divided by 2, that is going to be 320.5 at x, and in y again it is also same 320.5. Now we have to scale the value with respect to the equivalent static method. So for equivalent static method at x we have 1452.08 divide by 320.5. So that is 4.5 is the scale factor in the x direction, and in y direction 1742.49 divided by 320.5. So that is going to be 5.4. So these are the scale factors for time history analysis. Now I'll show the hinges generated and the performance level. We'll go for display. Deformed shape. So here we will consider the pushover at x direction, step 0. So here it is the curve which we saw as ABCDE, And we can even focus on the this one, the immediate occupancy, life safety and collapse prevention will apply to the model. It's been applied. So I think so at step 4 we can, I think it's in step 4, we can see the hinges like collapse prevention takes place at these joints. I think in this span this two column fails, and here again that column also fails. So we'll go for step 6, 7. So you can see the hinges being generated. So based on this, we can come to a conclusion the performance limit of the structure. So we have, critical. I think it's 4 columns are critical. So we have to either increase the dimension of the column or the reinforcement and other stuffs. When we increase, we can protect the structure. So we'll unlock this model. We will do the scale factor for time history analysis. We'll go for define. So in define, load case, here we'll go for the time history, modify. For at x direction it is going to be 4.5 as a scale factor. Click OK, and here we'll click modify, and now here in this direction it is going to be 5.4. Okay. So now this time we are going to run only the equivalent static method and the time history. All other cases we are not going to run. So we'll make them not to run. So two cases. So time history at x and y, and at earthquake at x and y. So these 4 load cases only we are going to run. Click run. So you can ignore these 2 cases in time history. So they have not considered, it is telling that they have not considered the non-zero time history function. Again, we can ignore these 2 conditions. So we'll check for the results. So we'll go for show tables. Click OK. So again, their values are quite near. So it is matching. The equivalent static at x and y are quite near. So again, this is correct. I would like to thank Dr. V. Vasuki ma'am for giving me this opportunity to share the knowledge with the students. Thank you ma'am, and thank you students.